Imagine this, you just start your plant design job as a chemical process engineer and your boss asks you to do the design of a liquid control valve. Which characteristics and which information you should consider to do or to finish this task. If you want to know more about chemical process engineering plant design, this video is for you. My name is Jeferson Costa. I'm a chemical process engineer with expertise in plant design and responsible for the INPROCESS Booster training program. In this video, I will share with you an evaluation of a paper discussing about the pressure drop needed to design a control valve for liquid servers. This paper was developed by Frank Yu to the Hydrocarbon Processing magazine and discuss what the chemical process engineer should consider as pressure drop in a control valve for liquid servers. You will see that the author covers the sizing of the liquid valve based on the CV and based on each type of control valves that can be used. For instance, globe valve and rotating valves types, and which are the considerations that the chemical process engineer should add to the specification in order that the instrumentation engineer can select the proper control valve. But to understand the paper, I will share with you also some other information. So in this video, I will cover at least 6 topics. What is a control valve? Who design, size or select control valve design conditions, what is CV, control valve operating range, and I will show you in the INPROCESS how you can do a valve rating. All of these in the point of view of a chemical process engineer working with plant design. Let's begin with what is a control valve. In simple terms, a control valve is a manual valve with an automatic actuator. That means that instead of having an operator to regulate the opening of the orifice that has in a control valve, the actuator does that automatically based on the present value in the controller that is associated with the control loop. The way of controlling the process is based on the pressure drop. So for different kinds of control valves, valve, butterfly valve, globe valve, you will have a pressure drop associated to that. And because of this pressure drop, it's possible to regulate the flow to get the desired conditions for the set point. For instance, I want to control the flow, so based on the opening of the control valve, I will have more flow or less flow, and I will measure that and inform to my control loop in order to reach the desired set point. On the other hand, you can, for instance, want to control the pressure. So the same pressure drop, you will regulate the opening, open more, closing more, to have the desired pressure downstream or upstream of your control valve. You can also want to regulate the temperature. So based on the pressure drop, you will have more flow or less flow, and this media can heat or cooling a process, and you will control the opening in order to get your desired set point for your process variable. The main purpose of the control valve is to remove the operator from the field, because this way, based on the changes in the process, the actuator will do an automatic action to regulate the orifice. And when we are chemical process engineers working with plant design, the first place where you will consider having or not a control valve is in your process flow diagram. It's when you are developing a new process or you are developing plant design, you will start with process flow diagram, and there you show the main control loops that you have in your process. It can be liquid control, flow control, temperature control, pressure control. Most often, we have at least the main controls in your process flow diagram. When you proceed with the design phase of your project, you will need to show the control valves in your piping and instrumentation diagram. There, you will have a complete or a full control loop with the control valves with the transmitter, with the primary element for measuring the flow or the variable that you want to control, and etc. But although you have these two documents, these drawings, as a deliverable from the process engineering department of the process engineering discipline, you will not buy or you will not install a control valve based on that. To buy your control valve based on a specification, and that specification comes from your heating material balance as the primary source for the process conditions. Moreover, you need to consider also other requirements and information based on the fluid that you are using, the location that it will be installed. To have a control valve installed in the field, you have a long path to run, and everything starts with the chemical process engineer in plant design. And that leads to another question: who do the design, sizing, or selection of control valves? In terms of chemical process engineering plant design, we don't do design of control valves. Design of control valves are associated with the mechanical design of the component. And who does the mechanical design of the component is the vendor. It can be Samsung, it can be Heater, or other control valve supplier. So we don't do the design of the control valve. We don't do also the sizing of the control valve. Although we do calculations for the CV, in fact, what we do is the selection of the control valve. We go to the market, we evaluate the vendors, and based on the process conditions, we select the best control valve to fit to our needs. And depending on the company that you are working on, if it is big, small, or medium company, the responsibility for doing the selection of the control valve will vary. In medium to small companies, for instance, most often the chemical process engineer are responsible for doing the selection of the control valve. And the selection, there are more information to be added to the selection of the control valve than just the process conditions of your process. But depending on the company, the responsible for doing the specification and consequently the selection of the control valve is the instrumentation engineer. In my previous job, I started as a chemical process engineer working with plant design. So because of the size of the company, my main duty was to provide the process conditions for the instrumentation engineer to perform the specification and selection of the control valve. But now, in my current job, I need to do not only the heating material balance to provide the process condition for the control valve, but also do the specification of the control valve. And that leads that I need to learn more about instrumentation in order to be able to do that. That has good points, weak points, but as much as you can learn for a job is better for you or is good for your career. And which are the minimal information that you need to have to do the selection of a control valve. If you are responsible to doing the selection of a control valve, you need to develop a specification sheet for that control valve. And one of the first information that you must add to that is information related to your fluid. Is it gas? Is it liquid? Is it two-phase stream? What is the stream that you are using? Is water, natural gas, ammonia, hydrocarbons, etc. And which are the conditions, the operating conditions for this stream? The pressure, temperature, flow, which are the composition of the stream, because based on all of these, you will get the properties of your fluid. And based on the properties of your fluids, you will do or perform the calculations for the CV. That is the main reference that you have to do the selection of your control valve. But not only that, you will not use only this information to do the selection of your control valve. As I told you, a control valve has an automatic actuator, and it can be pneumatic or electronic. So the environment where you are installing or you will install your control valve is also very important. If you are here with me up to this point, get this opportunity to subscribe to my YouTube channel if you didn't do yet. And most important, do your like to this video, because this way you will help me to reach 100,000 chemical process engineers around the world. As I told you, the main reference for selecting a control valve is the CV. But what is CV? Technically speaking, CV is defined as 1 US gallon per minute of 60 degree Fahrenheit water that flows through a valve with a 1 psi pressure drop. In normal terms, it means that CV is related to the flow of a fluid through an orifice to a specific pressure drop. So based on that, there are equations to define the CV based on the liquid's definition, but we calculate also the CV based on gas streams, gas flow. So the equation is a little bit different. In this video, we are talking only about the liquids. It's not my purpose here to get deeper in calculations, because what I'm teaching you here in my channel is to be a chemical process engineer, to work with plant design. So the concepts to understand how important and how to use is much more interesting to me to teach you than the calculations. What is important to understand here is that when selecting a control valve for an application, the calculated CV is used to determine the valve size and the trim size that will allow the valve to pass the desired flow rates and provide stable control of the process fluid. If you select a CV too small, or if you select a CV too big, your control valve will not work properly. And that leads to which are the control valve operating range. The operating range of your control valve will depend on the type of valve that you will install in your process. Is it a globe valve, a bow valve, butterfly valve, or other? Depending on the type, you will have different ranges of operations. And ranges of operations here, I'm talking about the percentage of opening. It can go from 0 opening, that the valve is closed, up to 100% opening. And remember that 0 opening or 100% opening, you are not controlling anything. So depending on the reference that you get, eventually you will find that for globe valves, operating range from 20% opening up to 90% opening is a good range of operations. You can find also some references telling you that for a bow valve, 15 degrees of opening up to 90 degrees of opening is a good range of control. And verify that now I'm talking about degrees of opening, because I'm talking about rotating valves. But you can convert that to percentage of opening, 0% to 100% opening. And there are references that will tell you that 15 degrees opening up to 60 degrees opening for a butterfly valve is a good range of operations. It's important to understand that different types of valve will give you different characteristics of control. For instance, a globe valve installed in your process will give you much more pressure drop than a bow valve or a butterfly valve. So if you are in a system that you need to control flow, for instance, and you have a very low pressure drop to lose in your process, eventually a globe valve will not be the best one to be installed. You will install a bow valve or eventually butterfly valve depending on the size of your pipeline. I worked in a process where the pressure drop between the flange of the process and the suction of the compressor was oversized, so we thought that would have much more pressure drop than in fact was during the installation, and it was selected for that service butterfly valve to control the flow in the process. But the main issue was that instead of having the control of the fluid, I need to add a pressure drop to the system because the discharge of my compressor had overpressure shutdown. So as the butterfly valve is not the best one to give you higher pressure drop, I had some issues in this process because I had override control loop where the control looked for the flow but also looked for the pressure upstream of the compressor, and because of that my control valve as a butterfly valve worked too close to the close position. It worked around 3% to 5% opening, and although I had enough flow to go through the compressor, my stability of the valve was not so good. So that is very important when you are dealing with plan design, is to evaluate this kind of situation to avoid this kind of mistake. And with that, we return to the paper because we need to calculate the CV of a control valve to do the selection of the control valve that fits to our process. And most often, what we do is get the design conditions, calculate the CV, and choose the valve where the operating point is in the middle range of the CV. For instance, let me show you a chart of a control valve. Here we have the Samsung valve size program, and based on the process conditions that I added to the program and with the medium properties, the software calculated the CV required for this system. And based on the CV required for this system, the software goes to the data bank of the Samsung and look for a control valve that matches the specification. So you can see here that the CV calculated is 1.38 and the software gives to me CV2, and I am able to evaluate the curve of the system. So the opening of this control valve is close or very, very close to 90% for this system. And this is a globe valve. So if I am in the design conditions and I considering to have a globe valve at 90% of opening, I don't have a margin to control my system if for any reason I increase the flow in 10, 20, or eventually 30%. And when I am doing plan design, I need to consider that kind of situation. That's why the paper says we must provide valve pressure drop at minimum, normal, and maximum flows to enable the selection of a proper valve for full operating range. Because based on the minimum, normal, and maximum flow, we will have different pressure drops to do the control of the process. Most often, what can happen when the engineer is selecting the control valve is based on the design condition, they will select a control valve that will be operating in the middle range of the acceptable range. So instead of having the operating point at 90% of opening, I will consider selecting a control valve with a CV that gives to me something in the middle of the range, around 60% for instance. So, and what I can do here is increase the CV size of this vendor. So instead of considering the purchase of a valve with CV2, I will consider a valve with CV5. and I will do the calculations again. I will keep the CV, the others information not. And with that, I have a control valve now. You can see that it is 0.5 inches. And if I go to the graph, now my operating point is between 60 and 90% of the opening. And the paper argues that to do the best selection of the control valve, you should do the calculation of the CV based on the maximum flow and the minimum pressure drop, and select this range of operation close to the limits of the acceptable operating range. And based on that, you will prevent the oversizing of a control valve, because as you increase the size of the valve, of course, that it gets more expensive, and you want to avoid that kind of situation. So to be able to evaluate what happens when you increase the flow, what happens with the pressure drop, I will share with you now high-seas process simulation where I performed case analysis to evaluate what happens if I decrease my flow 50%. Let's suppose that my range of operations can go from the design conditions to 50% of flow and 120% of flow. So here what I have is a pipeline. I have a valve that represents my control valve in the system, and I have the pipeline downstream of the control valve. And what will define the pressure drop in the valve? It will depend on the variable that you need to control, but most often the downstream pressure that you need are specified. For instance, I must fill or I must feed a reactor with propane, so I have the desired pressure at the inlet of the reactor, or I need to fill water to a cooling tower, to a heat exchanger, and etc. So the battery limits or the destination pressure usually is specified. We have the source of pressure that depends on the system. You will calculate to give you enough energy to do the flow of fluid through your pipelines from point A from point B, and the available pressure drop in the valve will be a consequence of the losses of pressure in your pipeline from point B, from point A, from point B. And in this system, for instance, when I considered 1 cubic meter per hour of water, and I would like to evaluate the pressure drop of my control valve based on the changing in my flow. So I ranged from 0.5 to 20% or above the design conditions. And with that, I got 8 steps. So in my results, I have the variation of the pressure drop as a function of the flow. And of course that you can see that as I increase the flow, the pressure drop available in my control valve decreases because I have more pressure drop in the pipelines, and to compensate the pressure that I can lose in the system, I need to reduce the pressure drop in my control valve. So the paper says that to do the right selection of my control valve, I need to consider the maximum flow and which is the result pressure drop. Based on that, I will have the calculation of the CV, and I will choose the CV as close as possible to the calculation. To input this data in my software, my selection software from Samsung, I will consider the process conditions upstream of the control valve and downstream of the control valve. I will not consider the stream water in nor the water out, because that will be a function of my system. And I already have the desired conditions on that. 1 bar G at the discharge, and I have the source as 2.5 bar G. What will vary is the conditions at the inlet of the control valve. Here I have 2.48 bar G, and at the discharge I have 1.398 bar G. Just to round, I will consider that I have 2.5 bar G and the outlet 1.4. So I have the flow, I have the pressure drop, and I have the fluid characteristics based on the data bank of the software. And now let's verify the calculation of the CV. So for the design conditions, what I have is 2.5 going out 1.4. This is my design condition, but I need to add the conditions at maximum flow, and my inlet pressure will be different. So let's see what is the pressure available, the pressure drop available. When I increase the flow to 1.2 cubic meters per hour, now I have at the inlet of my control valve rounding 2.5 bar G, but now at the discharge of the control valve I have 1.6 bar G. So I will update that in my selection software. And I must consider also what happens when I have the minimum flow. So in this case, I will add the information for the minimum flow, that is half of the design flow. With this, I have 2.5 bar G at the inlet and now 1.1 bar G at the outlet. Now that all information, process information are informed to the software, I go to the calculations. So I will let the software do all the calculations, and I will not force the CV5. With this, we return to CV2, but let's verify the graph. We can see here in the graph that my point 2, that is the maximum flow, is above 90% of the travel. So what I will do here is increase my CV to move these operating points to the left side. To do that, I need to increase the size of my CV. So let's use 3. And now I will force the CV, but the other information I will let the system be calculated. So now I have a bigger valve. It was 3 and 8 inches. Now it is half inches. And let's go to the chart. And now at my maximum flow, my operating point is below 90%. So it is better than being higher than 90%. So in this case, I could use this control valve as the best one for my process, because the minimum opening is also inside the range between the operating range, acceptable operating range. And just I forget, software, as I told you, do the calculations of the CV. So we have 1.1, 1.46, and 0.5 for the minimum flow. And the INPROCESS also does calculations for the CV. So if I go to valve rating, I can calculate the CV required to the process. I just need to go to my valve and go to the ratings. When I do that, I choose the opening characteristics. In this case, we are considering equal percentage, and I use the valve opening as 100% to do the calculations of my control valve, and I click on valve size. When I do that, the INPROCESS will do the calculations of CV based on the methods that I want to, and here the calculations gets very close to the one informed by the Samsung software selection, 0.5 CV. Based on what you have seen, I believe that you can understand better the Frank Hughes paper, where he does a correlation between the delta P in a control valve, the CV calculated, and the opening of that valve, comparing a globe valve type with a rotary control valve type. And in the summary, what he finds is that in general, a rotary control valve has a wider range of flow than a globe control valve, except for a system with a smaller system pressure drop. So guys, this is it. If you want to know more about chemical process engineering and plant design, go to my website, jeffersoncosta.com, where you'll find the links to all my social media like YouTube, LinkedIn, Instagram, and etc. And I'll see you soon in the next video. Bye bye.